All right, let's get started. So welcome to the third lecture of CS294-112, Deep Reinforcement Learning. Today's lecture is going to cover optimal control, trajectory optimization, and planning. So this will be kind of a crash course on controls and also some discrete planning stuff. But before we get into that, a few announcements. So assignment 1 will be out next week. So we're getting that ready for you right now. Do make sure you sign up for Piazza. So currently there's substantially more students enrolled in the class than there are signed up for Piazza. So please do sign up because we'll be posting homework announcements. You'll need, for example, the Mujoko simulator for the announcements. So we'll tell you how to get a license for that and so on. So for that, if you're enrolled in the class, please do make sure that you sign up for Piazza to get those announcements. Friday section. So this Friday, we'll have a review section on things like automatic differentiation, stochastic gradient descent, and training neural networks. So if you have a bit of a background in deep learning, chances are you're okay with this. But if if you've never worked, for example, with TensorFlow or Theano before, it might be a good idea to come to this section and get all of your questions answered. If you want sort of a quick test to see if this section is something that you would benefit from, try the MNIST TensorFlow tutorial. And if you can do that, no problem, then you're probably in good shape. But if you have some questions that come up, please do come to the section. So it'll be on Friday at 10 a.m. And the room has been posted on Piazza, which is this. And Chelsea will teach this section. Okay. So let's talk about the material for today. So in the last lecture, we learned about imitation learning from a human teacher. So this is a sequential decision-making problem, but one where you actually get data from a demonstrator who tells you what you should be doing, and your job is to imitate that demonstrator. And then in today's lecture, we're going to start to work our way towards a situation where you don't need a human demonstrator anymore. Maybe you can have a machine demonstrating for you. So can the machine make its own decisions? That's what we're going to study today. How can we choose actions under perfect knowledge of the system dynamics? So if we know exactly how physics works, can we set up an optimization problem that will allow us to choose good actions? And when I say system dynamics, what I mean is this thing down here. So if you remember this graphical model from Monday, you have your observations, you have your states, and the system dynamics is how the next state depends on the current state in action. So if in today's lecture, we're going to assume that you know what this is. Maybe you have some equations of motion, you have knowledge of physics, or you have a simulator. And if you know what that is, can you choose the actions U to minimize some costs? And depending on the context, this is sometimes referred to as optimal control, trajectory optimization, or planning. Next week, we're going to talk a little bit about what happens if you don't know the dynamics. So if you don't know what this distribution is, can you, for example, learn from data and then do optimal control, trajectory optimization, or planning? So that's something we're going to cover next week. And then after that, we're going to talk about how we can use this to actually then learn policies using deep neural networks. And that's going to be kind of like imitation learning, only it's going to be imitating an optimal controller instead of a human. So that's going to be next week. And today we're going to cover point 2 up here. How can we actually make those decisions if we know the dynamics? Okay, so next week we'll talk about the policy. So today's lecture is going to cover the following topics: making decisions under known dynamics, some definitions and some problem statements, trajectory optimization, which is essentially just back propagation through dynamical systems. We'll talk about what we can do if your dynamics are fully linear, and I'll explain what this means. And I'll cover an algorithm called the linear quadratic regulator. Some of you might already know about this, but I'll cover this to kind of give you a little bit of a crash course on some optimal control stuff. I'll talk about how this can be applied to nonlinear dynamical systems, which is kind of most of the complex continuous systems we have to deal with. And then I'll talk about another algorithm for choosing actions in discrete systems, and I'll cover this algorithm called Monte Carlo tree search. And then I'll present another little case study from a recent research paper that uses Monte Carlo tree search and learns some deep neural network policies. So most of the technical material I'll cover in today's lecture is not actually deep learning or deep reinforcement learning related, but it's kind of good background to have to try to understand some of the stuff that'll come later in the course. So here are the goals for today's lecture: understand the terminology and formalisms of optimal control, and understand some standard optimal control and planning algorithms. So it'll be kind of a sampling of these things, and I'll point out some other papers and surveys later on if you want to get more in-depth details about this. And today's lecture is going to be a little bit more math heavy than the one on Monday, so please do try to follow along. And if you get lost, if you have some questions, just go ahead and ask. and I can cover things in a little bit more detail on the board. All right, so this is kind of a recap from Monday. If we don't have data from a human to tell us which actions we should take, and we just need some sort of notion of what it means for an action to be good or bad, we need to introduce some kind of cost function. So on Monday at the end of the lecture, I mentioned that if you have this situation where you see the picture of the tiger and you need to choose your continuous action, you have something that you want or don't want to happen, and you're trying to let's say, for example, minimize the log probability of getting eaten by the tiger. So you have some kind of event that you'd like to have or not have, and in general, you can express that event, that desire to have or not have that event, as a cost function. So the kind of general statement of what makes an action good or bad is that it's the sequence of actions that's going to minimize the total cost. Now, it's important to remember that this is a sequence. So you might choose some initial action that has very low cost, but puts you in some really bad state later on, where you'll incur high cost. So you need to consider the entire sequence to do this right. And in general, in the deterministic case, you can write down the resulting optimization problem as this kind of constraint problem, where you're minimizing the total cost over the length of your existence, subject to this constraint that the next state is going to depend on the previous state in action, according to the dynamics function f, which, as I mentioned, we'll assume is known for now, but we'll deal with the unknown case later. So we have this cost function, and I mentioned that sometimes you can also have something called a reward function, which is exactly the same. It's just the negative of the cost function. So in today's lecture, I'll mostly use the term cost, but if you hear the term reward, just mentally put a negative sign on that, and it's the same thing. Oftentimes, in the world of optimal control, we use cost functions. In the world of reinforcement learning, we use reward functions, but don't let that confuse you. OK, so let's deal with this problem a little bit more. Yes?
Is the reason why you're not using expectation is it because the dynamics are deterministic?
Yeah, so I'll mention the stochastic case a little bit later, too. Yeah, good question. All right, so let's deal with this optimization problem a little bit. Let's kind of try to break down what's going on here. So you have an equality constraint in there, which means that you can just substitute this equation for xt into the objective, and you can write it down as an equivalent unconstrained problem, which can be pretty convenient. So in the unconstrained problem, it's not particularly complex. It's just a little complex to write down because you have this f of f of f of f, but it's basically just substituting that constraint into the objective. And now no more constraints. So it's a big unconstrained problem, which is the sum of these costs over all time, where the state is given by the f of the previous state, and you can kind of just substitute these in there. So it's unconstrained, which is good. And then while there's a pretty substantial number of different optimization algorithms for solving this kind of problem or this kind of problem, at a very, very high level, they basically boil down to some version of differentiating through this thing and using backpropagation to optimize. So if you're familiar with neural networks and backpropagation, it's basically going to be the same story, but the details are going to change up a little bit in order to achieve the best results. So if you retain nothing from today's lecture, just remember, write down the problem, differentiate, and backpropagate. So in order to do that, we need to know a few quantities here. We have two functions. We have the c and we have the f. So if we want to differentiate them, we need to know their partial derivatives. So we need to know the derivative of f with respect to x, the derivative of f with respect to u, and the derivatives of c with respect to x and u. Sometimes if we want a higher order optimization method, we might even want to know the second derivatives. So if someone refers to a linearization of the system dynamics, what they're talking about is df dx and df du. Now, in practice, it really helps to use something that looks like a second order method because you're essentially backpropagating these derivatives through a big, long chain of these f's. So if you use standard first order methods like standard gradient descent, the conditioning here might be pretty bad, and you might have a lot of trouble getting a good solution. It's sort of the same reason, those of you that are familiar with recurrent neural networks, it's the same reason that optimizing recurrent neural networks is kind of tough, because you're backpropagating through time to this complicated dynamics. So in practice, it really helps to use a second order method. Now, if you dig a little bit into optimal control techniques, you might encounter some terminology, and I just want to kind of give you a brief overview of what this means, just so that you're, when you see it, you know what it's talking about. You might hear the term shooting method or collocation method. Shooting method at a very high level basically refers to optimizing over the actions and treating the states as a consequence of those actions. So that's basically this thing, where you substitute that constraint into the objective, and the only things that are variables you're optimizing over are the u's. So if you're optimizing over the u's, and you're substituting in f of x1 u1 for x2, and there's no more constraint, that's typically referred to as a shooting method. And the reason it's referred to as a shooting method is that you choose the action at step 1, and that's going to wiggle this whole trajectory around for the rest of the time steps. So it's sort of like you're choosing which way to shoot at that first time step, and that's affected what happens next, and then you're choosing something at the second time step, and that affects everything that happens next, and so on. So shooting methods are nice because they're simple. You can write them down as an unconstrained optimization, but sometimes the sensitivity of the trajectory of that first action can be quite large, and the sensitivity of the second action is large, and so on. So sometimes they don't have the most favorable numerical properties. If you see the term collocation method, typically that refers to a situation where you actually keep the original constrained optimization problem, and your optimization variables include the actions and the states. So if you want kind of to put a picture with this, you have all these dots along your trajectory. These are your states, and you're directly going to move those states around while keeping the actions and states such that they satisfy this constraint. And these kinds of problems are sometimes solved by things like sequential quadratic programming algorithms. So today we're going to actually talk about a shooting method, and I'll leave discussion of collocation methods for you to read on your own. And in particular, I'm going to talk about a class of algorithms based on the linear quadratic regulator, which is a fairly simple class of second-order techniques for trajectory optimization. So before I get into a discussion of kind of the general nonlinear iterative LQR algorithm, I'll present a simplified version for linear dynamical systems. And some of you might have seen this if you took a robotics class or an optimal controls class. So in the linear case, we're going to make a simplifying assumption about the dynamics of our system. So we have this unconstrained optimization problem, and we're going to assume that our dynamics F is actually linear, meaning that it's some matrix times the concatenated vector of states and actions plus some vector. And this matrix and vector might be time dependent, so they might be different at different time steps, but it's linear. So if you want kind of an example of what a linear dynamical system might be in the physical world, let's say that you have, can everyone see this? Yes? OK. So let's say that you have a little box, and you have a ball in there, and that ball is kind of bouncing around in the box. It's in space, so there's no gravity. OK? So the ball has a state that consists of its position, x comma y, and it also has a velocity. So it has x dot and y dot. OK? So its state is four-dimensional. And maybe your action is a force that you can apply to this ball. Maybe this is like billiards, and you can push it. So maybe you have a force xu, or I should say fx, and fy. Okay. So if you want to write down a linear dynamical system for this, if it's just moving around in free space, you can write down its equations of motion. It'll be quite simple. So it'll be like this: x t plus 1, y t plus 1, x dot t plus 1, and y dot t plus 1. That's the next state, is going to be equal to, well, let's write this out. So the first one is going to be xt plus delta t times x dot t. You have to kind of choose how your equations of motion here. There's different integrators you can use, but I'll just write down a very simple one. So delta t times x dot t plus 1/2 delta t squared fx. Maybe you're assuming that it has a mass of 1, so force directly translates into acceleration. Okay? So this is your next position. The y is the same way. So we're all good with that. And then for velocity, it'll just be xt dot plus delta t fx and yt dot plus delta t fy. Okay? So now you'll notice from these equations that this thing is just entirely linear in the state at time t, which is xt, yt, xt dot, yt dot, and the action at time t, which is fx and fy. And you can write down the resulting dynamics matrix. It's just going to be ft is equal to 1, 0, delta t, and then the action part is going to be 1/2 delta t squared, 0. Okay? And then down here you can have 1, 0, 0, delta t, 0, delta t squared 1/2, and so on, right? So you can basically write down a matrix such that this thing holds. So that's just a simple example of a linear dynamical system. So it's a real physical system where it just so happens that the next state can be expressed as a linear function of the previous state. Just to give you an example. And then, of course, if this ball is not in space, if it actually hits a wall or something and bounces off, then at that one time instant, there's going to be something funny going on here, like maybe the velocity will actually be negated because it's bouncing off in the opposite direction. So at that one time step, something really strange is going to happen, but at all the other time steps, these dynamics are going to hold. So that's important to know, that those dynamics can be time varying. OK, any questions about this? OK, great. So linear dynamics. And then we'll assume that our cost is a quadratic function of the state. So maybe it's the distance to some desired goal position or something like that. And so it's going to have a matrix, capital C, and a little vector, lowercase c. OK, so linear dynamics, quadratic cost. And that's why this is referred to as the linear quadratic regulator, or linear dynamics quadratic costs. So these are the equations we have. And from here, we can actually compute what the optimal actions should be. And I'll go through the linear quadratic case, but then I'll tell you how the same algorithm can actually be used for arbitrary nonlinear dynamics. So this is a dynamic programming algorithm where you actually start at the end of your trajectory with the last action, u capital T, and then you actually go backwards through time and compute a rule that'll give you all the actions in between. So let's start with the base case. If you just want to solve for the last action, u capital T. So this is the only term that depends on u capital T. It's the very last cost, where you have the state, which is some complicated function, and the action, which just goes right in there. So that's the only term that depends on ut. And let's write down this thing, which we'll provocatively call q of x dut, and why we call that q will be more apparent later. But for now, this is basically all the stuff in the objective that depends on u capital T. And it's just the cost of the last time step. So it's some constant plus all the cost of the last time step, which I just substitute in there. And then we can just write down the gradient of that, right? So we can take this equation, differentiate it, and set the derivative to 0. So if you differentiate it, there's just a linear term and a quadratic term. So that's the derivative. So this is the part that I should tell you what those subscripts are. So the cost matrix, I'm going to write down like this. I'm going to say that it consists of 4 parts. There's the upper left quadrant that's dependent on state, the lower right that's dependent on action, and these cross terms in between. Does this make sense to everybody? Yes? OK. So if I use these symbols to denote the 4 pieces of that matrix, then I can write down the gradient with respect to u like this, right? So this is just the part from the cross term. This is the part from the quadratic term. And this is the part from the linear term. And that's equal to 0. So now I can just solve for ut. Ut appears in just one place in that equation. So if I solve for ut, I just have to throw all the terms that don't depend on ut on the right, and then multiply by inverse of c ut ut. So that gives me this equation for the optimal u. OK? This is just very simple, just the optimal of the optimal u for a quadratic function. It depends on x here, but otherwise we're all good. So now we can kind of express this in a slightly more convenient form to avoid all this messy notation. We can just say that ut is going to be some linear function of xt plus some constant. And specifically, the linear function is this part. So that's just this inverse and this matrix. And the linear part is just the matrix and this thing right here. OK? So now we have a very kind of conveniently simple equation that gives us the last action if we know the last state. And now we can just eliminate the last action from this optimization, because all we need to know is the last state. OK. So that's what we have so far. And now we can basically eliminate the last action. And then what we're going to do is we're going to write down the same objective up here, but now without the UTs. So we'll basically take this equation for UT, kt xt plus little k, and we'll substitute that in here. So all I've written out down here is just this thing with this equation substituted for u. Okay, so there are no more u's, there's only x's. And now I can use the fact that this c can be written with 4 terms to write this really horrible, messy function. It's a really, really horrible mess, but I've sort of conveniently written out for you here so that all the stuff in this top row is quadratic in x, and all the stuff in this bottom row is linear in x. So that means you can just collect all the quadratic and linear terms and write your objective as just a quadratic term in x and a linear term in x, where the matrix for the quadratic term is this horrible mess, and the matrix for the linear term is this horrible mess. So it's a lot of symbols, but it's actually a very simple expression. And I've also provocatively called this v, which is going to denote value function. But I'll get into that later. OK, so now we've we've taken this last time step, eliminated the action ut, and written out everything as just a simple quadratic function of the last state. And now we can go back one step. So now we're going to solve for ut minus 1 for the second to last action. Now ut minus 1, unlike ut, is not, it doesn't exist by itself. It actually affects the next state xt. So we have to account for that. But it affects the next state xt in a known way through this dynamics matrix, right? So we can write down xt as a function of ut minus 1 and xt minus 1. And now, if we just get the part of the objective that depends on ut minus 1, it's the cost at step ut minus 1 plus the effect that ut minus 1 will have on the last state. And that's just captured by that function v that we derived on the previous slide. So now, that's the function v, just to remind you, with these terms that were given on the previous slide. And then we can substitute in this equation for xt, this ft minus 1 times this vector times this thing. And now we can just substitute that in here and get this expression for v xt that's entirely a function of ut minus 1 and xt minus 1. So again, it looks like a mess, but it's just a simple substitution. And it has, again, a quadratic part and some linear parts. So again, everything is quadratic and linear. So we substitute that in there, and then we can just collect the terms. So there's a quadratic term here, a quadratic term here, and we can collect these into one quadratic term. There's a linear term here and two linear terms here, so we can collect those over here too. And those are the expressions for the matrix part and the vector part. And just like before, we can write down the gradient, set that gradient to 0, throw all the terms that don't depend on ut minus 1 on the right side, hit it by this quadratic term inverse, and solve for the optimal ut minus 1. And as before, it's some linear thing in xt minus 1 and some constant thing. And those are the linear and the constant parts. OK, so does the recursive step make sense to everybody? Does anyone have any questions about this? OK, great. So here's basically the algorithm now that we've seen the equations. We're going to start at the very end of the trajectory, and we're going to recursively proceed to the beginning. At every time step, we'll compute this matrix Q and this vector little q, as shown on the previous slide. We'll write down our quadratic objective for the action at that time step. We'll find the optimal action by computing the gradient, setting it to 0, and then solving. And that'll give us a linear term, capital K, and a constant term, lowercase k. And then we'll compute these v's so that we can get rid of the action at that time step, get this value function, and then proceed to the preceding time step. And then we repeat. So now basically we start at the end and we compute the action as this linear function of the state at every time step going backwards until we get to the very first time step where we have the very first action as a linear function of the very first state. And the very first state is known. So we actually now have the very first action. So then we can just perform a forward recursion. So we sort of computed these linear terms going backwards, and now we can zip them back up going forwards and get actual values for those actions instead of these equations. So for time step t equals 1 to capital T, we compute the action as a linear function of our known state, compute the next state using our known dynamics, and repeat. So now we've gone backwards, computed these linear equations for the action, and then we go forward and we get values for those actions. And now we've solved our optimization problem. Some useful definitions, I've kind of alluded to this as I went along. So this thing is called Q because it's actually the Q function. So it's the Q function is the total cost from now until the end of the episode if you're in state xt and you take the action ut. And this is for the optimal policy because you're computing the optimal policy as you go backwards. And the value function is the total cost from now until the end from state xt, which is just defined as the minimum of the Q function with respect to the action. And these definitions will come up again and again when we talk about reinforcement learning too. OK, now there was an earlier question about what happens if you have stochastic dynamics. So if you have stochastic dynamics, one thing you can do is you can say, OK, well, maybe my stochastic dynamics are actually Gaussian. So if your stochastic dynamics are Gaussian, where the mean is this linear thing and the covariance is some constant covariance, you can actually still choose actions according to the same rule as before. And it turns out that because of the symmetry of Gaussians, actually the same exact algorithm will compute optimal actions for you. If your dynamics are not Gaussian, or if the covariance depends on the action in some way, then this doesn't quite work. But if it's Gaussian with an independent covariance, then all is good, and you can just use the same exact algorithm. The state is no longer deterministic. Your state marginals are actually now Gaussian, but you can actually work through the math, and it turns out that all the same stuff holds. So if you want to check this as an exercise on your own, the only thing that you really need to remember is that the expectation of a quadratic under a Gaussian has an analytic solution. It's kind of neat. It just has this trace term with the covariance. So if you want to look that up, then you should be able to derive this on your own. OK, so that's the linear case. Now let's talk about the thing that's maybe more interesting in practice, which is the nonlinear case. When you have an arbitrary dynamical system, like a complicated three-dimensional robot that's experiencing frictional context, gravity, all this stuff, can we still use a similar algorithm and get a solution? So this is the nonlinear case, which is sometimes referred to as differential dynamic programming or iterative LQR. Those names might make a lot of sense. Iterative LQR because we're going to be doing LQR repeatedly, or differential dynamic programming because it's dynamic programming and it's going to use the derivatives of the dynamics. So these are the linear quadratic assumptions that we had before. We had assumed that our dynamics f of x t ut is some matrix plus a vector. So in the nonlinear case, what we're going to do is we're going to iteratively approximate our dynamical system as a linear quadratic system. And if you have something that's not linear and you want to approximate it as linear, or something that's not quadratic and you want to approximate it as quadratic, well, what you do is you do a Taylor expansion. And that's what we're going to do. We're going to take our dynamics and we're going to just compute their derivative and sort of approximate them around some states and actions using their linearization. And we're going to take the cost and we're going to approximate it around some reference states x hat and actions u hat as a quadratic using their Taylor expansion. So the idea is that you're iteratively optimizing your trajectory. You have your current guess at the states and actions. You linearize your dynamics around those states and actions. You quadrasize your costs around those states and actions. And then you improve your actions. So now all of the expressions here are in terms of xt minus x hat or ut minus ut hat. So we're going to introduce a symbol for these. We're going to call that delta xt and delta ut. And now this is just a linear quadratic system, but in terms of a different set of variables, not in terms of x and u, but in terms of delta x and delta u. So these are the deviations from the current x hat and the current u hat. I'll put this all together into a complete iterative algorithm at the end, but I just want to go through the details first. OK, so now you have sort of an alternative dynamics on these perturbations delta and an alternative cost on the deltas. And of course, the matrix here is given by the derivative of the dynamics. The matrix here is the second derivative of the cost, and the vector here is the first derivative of the cost. So everything is good with the world. We're back into linear quadratic land, and we can use the same LQR algorithm to compute the optimal delta ut around this reference trajectory. So that's our delta, and now we're going to run LQR. So here's a simplified version of the iterative LQR algorithm. So you repeat this until convergence. First, you estimate your linear dynamics using the derivative of your nonlinear dynamics. You estimate the linear part of the cost as the derivative of the cost. The quadratic part is the second derivative. Then you run the LQR backward pass on this modified deviation form of the state and deviation form of the action. You get you run the forward pass to compute these should be delta u. So you run the forward pass, and the forward pass you actually run through the real nonlinear dynamics. So when you actually step forward, you actually step through the true nonlinear dynamics to get the actual states that you will encounter. That way, your state x hat will always be a real state that's dynamically consistent. And then you update x hat t and u hat t based on the states and actions that you actually saw during your forward pass. So now you've changed your nominal trajectory, and then you can repeat. So linearize the dynamics, quadrasize the cost, run LQR, with a forward pass using the true nonlinear dynamics, get updated actions, and then repeat the process. Seems kind of straightforward. And why does this work well? Yes?
It's like sort of like Newton's method.
That's what I was about to say. Good question. Yes?
So how exactly do you choose your x hat and u hat?
So initially, you need to initialize it somehow. So initially, you might choose maybe your u hats are all 0. You run a forward pass with those u hats and get the corresponding x hats. Or you might choose your initial u hats to be random. So you need to initialize something that has to be dynamically consistent, meaning that the next state has to actually be f of xt ut. There was a question about Newton's method. So why does this work? Because we're going to compare it to Newton's method. Good question. So let's compare what I had on the previous slide to using Newton's method to optimize some function g of x. Well, what is Newton's method actually doing? Okay, we're going to approximate g of x with this with its gradient. We're going to and its Hessian, and then we're going to minimize a quadratic function where the Hessian gives you the quadratic part and the gradient gives you the linear part, so that's just the Taylor expansion of that function. We solve for the x that minimizes this quadratic thing, and then we repeat. So that's essentially Newton's method. Iterative LQR is basically the same idea. You locally approximate a complex nonlinear function with its Taylor expansion. Iterative LQR is not exactly Newton's method, but it's an approximation to Newton's method, and you can make it exactly Newton's method with a little change, which is that you need to compute second derivatives of your dynamics. And I didn't get into that here because second derivatives of your dynamics are kind of complicated because your dynamics are a vector valued function, so the second derivative is a tensor, and then the linear algebra gets kind of messy. But you can actually do that, and you just get the linear term and then this kind of really complicated quadratic term, which is a tensor product. That's actually how the original differential dynamic programming algorithm was described, and that actually does reduce to Newton's method. Iterative LQR does not, but it tends to be a lot simpler in practice because computing these second derivatives of the dynamics can be kind of a mess. Okay, so now let's go back to this analogy to Newton's method. So this is the version of Newton's method I had on that previous slide. But we don't actually typically do Newton's method quite like this because it's a bad idea. Can someone tell me why it's a bad idea? H could be really big. Is there another reason? Okay. This is the kind of the pictorial representation of this. So let's say that you're over here and you have this really easy function, 1D function, and you fit a quadratic to it, and this is your quadratic approximation. And then you go to the optimum of that quadratic, and you end up here. So in reality, oftentimes when we use Newton's method or quasi-Newton algorithms, what we actually want to do is we want to do something like a backtracking line search in case the quadratic approximation was not good and it takes us a little bit too far. It's kind of similar to H being too big, right? Because if your curvature is too big, it kind of shoots you off into far away from your current location, where your Taylor expansion might no longer be accurate, because the Taylor expansion is only accurate locally. So in Newton's method, we would typically use something like a backtracking line search to make sure that we actually improve at every iteration. And we can do exactly the same thing in iterative LQR. So we can just take this step right here where it says run forward pass with this control law and put a little alpha over here. Why an alpha over here? Well, because as this alpha goes to 0, this term is going to go to 0 too, because you're not changing your action at all. This should be delta u, by the way. That's a typo. So you're not changing your action at all, which means that you're keeping the same actions as before. So you can just put a little alpha multiplier on the constant term, and that'll be your step size. So then you start off with alpha equals 1, you run the forward pass, and if it doesn't improve as much as you want, you maybe reduce alpha in some way, maybe divide it by 2. So there'll be a paper reference on a subsequent slide that describes sort of some good heuristics for tweaking the step size. Okay, so you search over alpha until you get the improvement you want. So here's some additional reading if you want to learn more about this algorithm. So this is the original differential dynamic programming manuscript by Jacobson and Main, which from the 1970s, that describes the original differential dynamic programming algorithm. If you want sort of a more modern, kind of accessible write-up on this, I would recommend this paper by Yuval Tassa and collaborators called Synthesis and Stabilization of Complex Behaviors Through Online Trajectory Optimization. And this describes the iterative LQR algorithm using similar notation to what I used in this lecture. So it's sort of a practical guide for implementing nonlinear iterative LQR. There are other ways to do to control the step size. So this is actually one of my papers from a couple of years back that proposes more of a trust region style method instead of a backtracking line search, which can be more useful if you're fitting unknown dynamics using real world data and you can't necessarily backtrack during the line search. So these are a few additional readings if you're interested in this algorithm. Okay, so next I'm going to talk a little bit about a case study that actually uses this stuff. But before I do that, does anybody have any questions about the technical portion of this lecture in regard to LQR, iterative LQR, or anything else regarding trajectory optimization? Yes?
Oh, can you give the equations for computing to say x hat t?
So for x hat t, let's go back to the form of the algorithm. So you run your LQR backward pass. Now you have this control law. And then you run the forward pass, and when you run the forward pass, you use the real nonlinear dynamics. And that gives you delta ut, this should be a delta ut at every time step, and a delta xt. And then you just compute new x hat t and u hat t by just taking the old x hat t plus delta x hat t. So just like in Newton's method, you get a sort of a, well, I guess the way I wrote Newton's method here directly gives you the new x hat, but you can also have Newton's method give you delta x, and then you just add it to your old x. OK, so let's talk about an example of a paper that uses this technique. There's no deep learning, there's no reinforcement learning going on here. This is just the optimal control stuff. But it's kind of cool to look at what it can do. So this is that synthesis and stabilization paper that I had on the previous slide. And what they're going to do is they're going to use iterative LQR with model predictive control. So model predictive control, or MPC, is a technique where every single time step when you're controlling your dynamical system, you actually replan the optimal trajectory. So I'm standing here right now. I'm going to run iterative LQR to determine my trajectory to walk out of this room. And then I'll take the first action along that trajectory. And then I'll replan all over again. That way, if something unexpected happens, I'm going to adjust my plan and act accordingly. So they're going to be using this model predictive control. And this is just sort of that written out as an algorithm. So you observe your state, you use iterative LQR to plan a sequence of actions, and then you just execute the first action, discard the rest, observe the new state, and so on. That way, if the state you observe is not what you expected, you're going to adjust your plan. It might not be what you expected if your dynamics were actually a little bit incorrect, or there's some unexpected perturbations. So here's a video from their paper. It's kind of cool to watch. They test this algorithm on a number of different dynamical systems in simulation. So this is kind of a benchmark acrobat system. This is a little swimming snake. This is a hopping robot. So the arrows that you see are unexpected perturbations that the human user is applying using a 3D mouse. So here is the kind of a more in-depth view of the acrobat. So first, it's just passively being simulated. Now the controller turns on and is trying to get it to stand up. And then they turn the controller off, let it fall, and then they turn it back on to force it to recover. So you can see it pretty quickly discovers these interesting behaviors. So there's no learning in here. This is just being optimized on the fly. And then here, they're going to kind of mess with it a little bit, apply some external forces, and make sure the controller can stabilize properly. This is a more interesting system. So this is a little swimming snake consisting of interlinked segments. And they're going to try to have it swim to the green dot while avoiding the red dot. So again, this undulating gait is basically emerging naturally as a consequence of the optimization without anything being pre-computed. So that's kind of nice because a lot of what we'll talk about in this class is going to involve pre-computing policies and things like that. But it's good to be aware of kind of what we can get if we know the dynamics and we just recompute the behavior on the fly. So here they just want to put the target far away to show that it does actually settle into a nice periodic gait. So here it's a monopod planar robot, and one of the authors on this paper really liked their 3D mouse, so they wanted to show off how they could push the robot around with their 3D mouse. And then, when they turn on the controller, it actually figures out how to stand up and how to balance on one foot, even when they push it around a little bit. Which is quite nice. I mean, this really nicely illustrates the flexibility of what you can do if you have a good model, if you have some way to get that good model, and then you recompute your actions on the fly. Now here what they're going to do is they're going to intentionally give the algorithm the wrong model. So they give iterative LQR a model with the wrong mass, so the real robot has a different mass, and they're showing that it still does something sensible just by virtue of being able to recompute the controls at every time step. So it can't quite stay upright because it's planning for a much lighter robot than it actually has. And this is sort of the most complex case that they tested, which is a 3D humanoid. And again, nothing is being pre-computed. They're just going to turn on the controller and tell it, I think, to stand up and then to walk. So first they want to show that it's passive, and now they turn on the controller and tell it to stand up. So this was a few years back, and back then it didn't quite run in real time. I think since then they've gotten this to run at real time or very, very close to real time. And the main computational challenge in these, by the way, is computing that linearization of the dynamics. So here, it's a physics simulator that cannot be differentiated analytically. So what they're actually doing is they're using finite differences to compute the derivatives of the dynamics during MPC. It's also just a lot of fun to play with these things. You know, when you have a policy that just does one thing, you can kind of just play it back. But when you have this thing, you can mess with it and see how it will react. All right. So that's model predictive control and iterative LQR. OK, so in the last half of this lecture, I'm going to talk about discrete planning. But before I do that, I think this would be a good time to take maybe a 2-minute break to let you guys relax a little bit. And I'll stay up here if you guys want to come up and ask me any questions. But 2 minutes from now, we'll resume. So the iterative LQR algorithm is just an algorithm for computing a sequence of good actions. And MPC is a way to use that algorithm to compensate for disturbances. So the idea is that if you just compute a sequence of actions, you execute those actions, and if something unexpected happens, you just keep executing the actions you planned. With MPC, you replan the actions every single time step. So that way, if you don't actually enter the state that you expected, you'll recompute your actions and do something sensible. So it's just basically online replanning. Yeah, so that's kind of actually the dark secret for these. That oftentimes for MPC, because they're under a very tight computational budget, they have to use a shorter horizon. And in order to get away with a shorter horizon, they need a more well-shaped cost. So if you remember the discussion of cost from Monday, it's basically that story, but like even worse, because now they need a cost that will cause the robot to do the right thing, even when it's looking only maybe like a second into the future. So for most of those behaviors, I think it was okay, but they have another thing at the end of that clip that I didn't show, where they actually have it walking. And for walking, they give it a cost that actually says like the center of mass should be over this foot or over this other foot, and so on.
You're not like lecturing.
It's fine. It'll be another minute.
I was also wondering the replanning. Does it also help avoid perturbations building up?
Yeah. Well, in general, if you don't replan, what you want to do is instead of directly executing the actions, you actually want to execute that linear feedback controller. So you know how there's this equation that u equals kx plus little k? So if you follow that control law, then you'll be better off if there's a perturbation. If you just directly compute the action and you just blindly execute that action, then perturbations will build up pretty badly. But if you follow the linear control law, that's a little bit better. And if you replan, that's even better.
All right.
I'm just curious. So iterative LQR, the delta is like the state here. Is it
Yes. Yeah. So the state is actually the delta x.
delta x? So you have to accumulate all the delta x.
Yes.
To actually get the
Yeah. Well, you can add them up as you go.
Okay.
Have people just tried computing the dynamics and then or learning the dynamics?
That's what I'm going to talk about on Monday. Okay, guys, let's get back to the lecture. All right, so we talked about optimizing trajectories for continuous systems where we can compute derivatives and things like that. So now let's talk about a different kind of system where you can't necessarily compute derivatives. So let's talk about discrete systems. So an example of a discrete system that many of you might be familiar with is the Atari games benchmark. So in Atari games, we have states, observations, and actions. Can anybody tell me what the observation in the Atari games is? Yes? No, that's the reward function. Observation. Did someone say something else? Pixels, exactly. So your observation is the pixels. And what's the state? this slide is labeled wrong, by the way. This is kind of unintentionally tricking you. But what's the state? Exactly, your memory, right? So it's a simulation of a small computer, and a very old computer with some number of bytes of memory. That's your state. That's the Markovian state. If you know the memory, you don't need to know the past. And then the image is actually your observation. Now, oftentimes, when you read papers that actually test on this benchmark, they sort of conflate the two, and they say that your state is actually your image. The reason that's kind of okay to do is because the image is actually almost Markovian for most of these games. So like over here with the Sequest game, once you see the picture, you actually pretty much know everything that's going on. But in general, this doesn't have to be the case. So there might be some hidden state that doesn't show up in the image, but does show up in the memory. So I'm going to abuse notation and do like the bad thing that I've told you not to do here. So I'm going to call the image the state. But just remember that really, if you want to be technically correct, the image is your observation, and the state is the state of the RAM of the emulator. And now from here on out, I'll keep calling it the image of state. So you have a discrete state. Whether it's RAM or whether it's image, there's only a finite number of these things because it's in a computer. You have a discrete action. You can push the up button, the left button. You can push the up button and the fire button. So there might be a number of actions, but there's a finite discrete set. So you have a discrete set of actions, a discrete set of images, and you can't really do something like compute the derivative of the image with respect to the action because that doesn't really make sense. So we need to do something else. So I'm going to present one algorithm that's fairly popular for solving these types of problems, which is Monte Carlo tree search. And Monte Carlo tree search is a heuristic version of a search algorithm. So if you remember from maybe an introductory programming class or an AI class, if you learn about heuristic search, that you can frame these discrete planning problems as search problems and try to solve them that way. So in general, if we want to solve this kind of problem using a search algorithm, what we might do is this. We start in some state. I'm going to call this S1. 1 means time step 1, not state 1. So the number here is indexing the time step, and you might be at different states in that time step. And then you can take both of the available actions. Maybe this is a simple world where you only have one binary action, so you can take action 0 or action 1, and that puts you into some states at time step 2. And then from there, you can expand all those out and so on. The problem is that if you search exhaustively like this, of course, it's going to be exponential in the number of time steps, so that's no good. But maybe what we can do is, for some of these states, like maybe this state over here, maybe we have some reason to believe that state is just no good. Maybe this is like a driving game, and this state over here, when you turn left 2 times, you actually just drove off a cliff. There's lots of different actions you can take after you drive off the cliff, but they're all kind of awful. So maybe we don't really need to explore that. Maybe we just run some sort of like reasonable default behavior there, and we just see, OK, this state is pretty bad. Everything here seems to look awful. So maybe you can approximate the value at this state over here just by running some base policy, maybe even just a random policy, and just get some rough estimate of how good that state is. It might not be a good estimate. Maybe there's some esoteric way to get out of this really bad state by climbing back up the cliff. But if you run some base policy from that state and it does something and it gives you a really awful score, maybe you say, OK, this state may be good, but most likely bad. So I'll just explore the other states that seem more promising. And this is really the main idea behind Monte Carlo tree search. So the Monte Carlo comes from the fact that these rollouts are going to be using some random policy. You can use a smarter policy there too, but the default versions just use random. So OK, so now we have a way to kind of guesstimate the value of a state. Maybe right, maybe wrong, but kind of a reasonable estimate. So now the question is, which of the paths should we search first? We can't search all the paths, so where do we start? Well, what we can do is we can run this base policy from one of the leaves of our tree, observe the score. Maybe this one, this trajectory where you take action 0 and then run this random policy, maybe that gives you a score of 10. And then you can run it from the other action. Say if you take action 1 and then run the random policy, that gives you a score of 15. So you can say, OK, maybe like this one is more promising, so then I'll expand this subtree a little bit more and leave this one until later. That could be a reasonable thing to do. By the way, when I draw trees like this, remember that this node, this is just what you end up with if you take action 0. This is not even necessarily a single state of the system. So if action 0 is stochastic, this leaf will accumulate all the things that happen for every time you take action 0, which might be random. So this is not really a state of the underlying MDP. This is a node in the search tree, and they're not necessarily the same thing. In a deterministic system, they would be the same thing, but in a stochastic system in general, they're not. And that's important to remember. OK, so the intuition behind the rule that we're actually going to use in Monte Carlo tree search is similar to this. We're going to choose the nodes that seem to be best so far, but with an additional twist, which is that we're going to give a little bit of a preference to nodes that we haven't visited very much. So if we've gone over here and we observe a 15, and we've gone here only once, and we've gone here only once before, maybe we go over here because this one looks better. But if we've explored the heck out of this thing, maybe we visited this like 10,000 times, and our average is 15, but we've only been over here once, and our average is 10, then we might say, well, yeah, this thing looks bad, but maybe we just didn't explore it enough. Maybe we should go back there and try a few more times, just to be sure that it really is a 10. So that's the intuition. And here is kind of a sketch of Monte Carlo tree search. So the first thing we're going to do is we're going to find a leaf of our current tree using this thing called the tree policy, which I'll explain in a second. Initially, when we start, we only have one leaf, which is our initial state. So then there's nothing to find. So we just start at the initial state. And then we're going to evaluate the leaf using some baseline policy, and then update all the values in the tree from that leaf up until the root with that new score. And then we repeat. And then once we're done planning with Monte Carlo tree search, then we just take the best action we came up with from the root. So let me kind of reveal this tree policy. So the tree policy is going to work like this. There are a few different choices here, but this is kind of a reasonable default. So first, if we're at a leaf that has not been fully expanded, meaning that we haven't visited both of its or all n of its children, then we just choose a new action arbitrarily, maybe randomly or maybe using some heuristic. Random works pretty well. So when we just have this root, the first thing we're going to do is we're going to expand both of its children, because not all its children have been expanded, which means we take action 0 and then run the base policy, and then we take action 1 and run the base policy. And what we're going to record when we do that is the total score that we've accumulated going through this leaf, which in this case I'll pretend is 10, and the number of times we've gone to that leaf, which is going to be 1. Okay? So now we're in a more non-trivial case. Now we have a root and two children. So if we're at a node where all of its children have already been expanded, then we're going to choose a child node with the best score. And there are a few different designs that we can use for this score. It's a bit of a heuristic design, but some are known to work better than others, and a few of them have some theoretical results as well. So what's a score we could use? Well, as I mentioned on the previous slide, we could just go with the best one. Here, both of them have been visited once, so it kind of makes sense that we go over here, because this one is a 12. So we'll go with action 1, and then when we're at that leaf, not all of its children have been expanded, so we choose an arbitrary action, in this case action 0, and expand it out. And maybe we find that here our total score going along this route was a 10. So now we say, okay, here we have a 10, and n is 1. But now we also have to update all the things on the route to the root. So up here we're going to increment it and say we're going to add that 10 to the 12, so this becomes a 22, and the number of times we visited this is 2. So the average score of this thing now is 22 over 2, which is 11. Okay? So we've updated everything from here on the route to the root. So now we have kind of a more complex situation. It looks like here, when we start again, and we're here at the root, we can either go this way or this way. Here the average score is 11, here it's 10, but this one has been visited 2 times. So now let's look at a score function that we can use. This is a score function that's going to encourage going to the best nodes, but also prefer going to nodes that haven't been visited as often. And this is a common reasonable default option for Monte Carlo tree search. Let me get into it a little bit more. So we have the q, which is the value at that node, divided by n, so that's the average value. And then you have this other term that deals with recency. And here's how you interpret it. The score of a node, it depends on the inverse of how many times it's been visited, but also on the log of the number of times that its parent has been visited. So the idea is that if the parent has been visited very often, but the child has been visited very rarely, then you should go to that child. If the parent has been visited very rarely and most of those visits went to the child, then you shouldn't visit the child, you should go to somebody else. Okay? So basically, the bigger the n of the parent, relative to the n of the child, the more you should prefer that child. The idea is that you don't want to just go somewhere simply because the parent has been visited many times. It has to also depend on the number of times the child has been visited. Any questions about this? Yes?
But why is it the log of the parents?
There's kind of a more in-depth explanation in the survey paper that I'm going to cite later. But kind of the short answer for a lot of these Monte Carlo tree search algorithms is that it's like a little bit of theory and a lot of empirical exploration. So there is a little bit of a theoretical basis for this kind of score. But the main reason that people use it is because it seems to work in practice for a lot of discrete problems like this. Any other questions? Yes?
Did you really just pick like a random default policy?
So it depends a lot on your task. Random is not bad because you're still going to, you're not just assigning that value to that node. You're still going to visit that node again if it looks promising and actually confirm that wasn't just sheer luck. Now, you can do a lot better if you use a smarter policy. And I'll talk about that a little bit at the end. But actually, yeah, using a random policy, depending on your system, can be OK. All right, so now we're in this situation. We have an average score of 11 here and an n of 2, an average score of 10 here and an n of 1. So maybe we decide that A1 equals 0 is a better action because we haven't been here as often based on our score. So now we go in here and we expand an arbitrary action. We measure the value. We add that value to its parent as well. So now this is what our tree looks like. Now these two look equal. So we pick one arbitrarily. Maybe we go over here. We measure an 8. And now this one is a 30 with an n of 3. So this one is clearly better because it's both less visited and has a higher average. So we'd go over there. And then we keep going like this until we hit our time budget. And then once we hit our time budget, then we choose the best action from the root and execute that on the system. So this is basically Monte Carlo tree search. Yes?
I wonder if that matters here because here you're considering all the descendants of your node, right?
Mm-hmm.
So why would the n st minus 1 be different?
Oh, no. So like if you're at this node and you're trying to choose whether to go here or here, nst minus 1 is the n here. nst is either this or this, depending on which one you're scoring.
Right, so nst minus 1 will be the same for
Yeah, so nst minus 1 will be 3, and yeah. Well, it's the same for both, but it's affecting how you trade it off against the score. So basically, if this thing is like, let's say, small, then it's going to count differently when weighted against the score. So it's just you have a constant here, but the constant is the same for all the nodes. Yeah. Okay, so that's basically Monte Carlo tree search. Here's a little bit of additional reading if you want to find out more about this algorithm. So this is a survey on Monte Carlo tree search methods, where you can find out about some of the motivation for that score function as well as other score functions that people have used. I don't actually have it on this slide, but one of the things that you might want to check out if you're interested in kind of recent applications of Monte Carlo tree search is the DeepMind AlphaGo paper, which used Monte Carlo tree search as a component in a larger system. So in fact, Monte Carlo tree search can also be used for games as well as MDP. So you can use it for adversarial games where it's a very natural setup. It's the usual thing with that you have with, for example, with min-max trees where you alternate between actions of one player and the other player, and that's a perfectly reasonable way to do Monte Carlo tree search as well. And in fact, it tends to work quite well in those regimes. One of the things that they did in the Go work was they actually used a much smarter policy rather than a random policy. So they actually used basically the learned policy for their system, but Monte Carlo tree search to choose to basically actually search over the first few actions and then use the policy to score the actions at the leaves. So that's kind of a nice way to combine a little bit of planning with a little bit of learning. What I'm going to talk about in this lecture is actually a slightly different, a slightly older paper because I didn't want to get into all the game theoretic stuff. So this is actually a paper that uses Monte Carlo tree search for Atari games. And what they're doing is they're doing imitation learning for Monte Carlo tree search. So they're actually going to use Monte Carlo tree search to figure out how to take good actions to play Atari games, and then they're going to train a convolutional neural network policy to then be able to perform good actions directly from images. And what they're using, they're actually just using Dagger here to ensure that that the final neural network policy does the right thing. So if you remember from Monday's lecture, if you just directly imitate an expert, whether that expert is a human or Monte Carlo tree search, you have this distribution mismatch problem. So to address that distribution mismatch problem, you might want to actually gather data from your learned policy, but then label that data using the expert. So the expert here is not a human. The expert is actually MCTS. So they're just going to take the observations that their neural network policy observed, basically the game states that it visited, and run MCTS from those states to label them with the optimal actions. And that's going to allow them to train up a good ConvNet policy. OK, so why do they train a policy? Well, there are a few somewhat complex reasons for this, some of which we'll get into in the lecture on next Wednesday. But in the paper, their motivation for this is that MCTS is a little too slow for real-time play. since you have to expand out all these nodes, and the more you expand, the better your action is. So in general, it's hard to get it to be real time. So if they kind of distill it down into a ComNet policy, it'll be able to run in real time and be useful for playing Atari games. But there are actually many other reasons why we might want to learn a policy from an optimal control expert. For example, our optimal control expert only really needs to generate data at training time. Maybe at training time, we might have more knowledge about the system. We might have maybe ground truth state information, some kind of external observer that tells us something that we don't know at test time. Maybe we might want to train a policy for the sake of generalization. So maybe we train in some situations where we can run optimal control, but then at test time, it might encounter new situations where the neural net needs to generalize. So these reasons for wanting to do imitation from optimal control or planning are things that I'll cover a little bit more next week. All right. So to conclude this lecture, the last thing I'm going to leave you with is this, that so far, we've assumed for iterative LQR, for MCTS, and so on, that we know how the system works. We basically have a model of the physics or of the video game emulator, or something that basically tells us what the next state will be as a function of the current state in action. In many cases, this is actually very reasonable. So if you imagine, let's say, building a policy for an autonomous car, you kind of know the physics of the system. You know that if you turn the steering wheel left, it'll go left. If you turn it right, it'll go right. So it's actually reasonable to assume that you have knowledge of the system dynamics. But in some cases, that's not a reasonable thing to assume. For example, if you're doing a robotic manipulation task and your robot needs to fold some towel, well, the physics of that thing are actually pretty complex. And more than that, if you actually want to know the physics of this particular towel, understanding its material properties and so on, that can actually be very, very difficult. So it'd be really nice to be able to deal with cases where we don't know the dynamics to start with. So that's what I'm going to cover next week on Monday, is how we can actually learn dynamics of our system so that we can then do optimal control or planning, and also how this model learning will interact with the planning or optimal control algorithm, and what we need to do to ensure that we get a model that's actually good for the optimal control algorithm that we're using. So that's going to be next week. All right, and that's it for today.